Nobody told you the universe was hiding something from you. That's the first problem. You walked in here tonight thinking physics is a subject, the way chemistry is a subject, the way history is a subject, something with a beginning and a middle and a syllabus that ends before finals. And I am here to tell you that is not what this is. What physics is, what it has always been, is an argument, a very long, very loud, very personal argument between human beings who cannot agree on what is actually real. And that argument is not over, not even close. In fact, in the last 30 years, we have discovered that we were wrong about something so fundamental, so load-bearing to everything we thought we understood, that I want you to sit with that discomfort for a minute before I start trying to fix it for you. Because if you let the discomfort in, what comes after it is not confusion. What comes after it is the most extraordinary thing a human mind can experience. The actual shape of reality, stripped of every comforting story we told ourselves about it. So, here is the problem, and I mean this literally here, in this room, in your body, in the chair you are sitting in. You believe, with total confidence, that the world you are experiencing exists in 3 dimensions of space. You believe that events happen in sequence, one after another, in something called time. You believe that objects have locations, that information has weight, that the past is fixed and the future is open. You believe these things not because anyone taught them to you, but because every cell in your nervous system has been shaped by millions of years of evolution to believe them, because believing them helped your ancestors survive long enough to produce you. And because of that, these beliefs feel less like beliefs and more like the walls of the room you are sitting in. They feel like the structure of reality itself. They are not. They are a very useful, very low resolution map of something far stranger. And tonight, I am going to show you the territory. Let me start at the bottom, because that is the only honest place to start. What is the universe made of? Not at the level of atoms we handled atoms 100 years ago. Not at the level of quarks we handled those in the 70s, more or less. I mean, at the absolute bottom, at the most fundamental substrate. What is the universe actually made of? And the answer that has been slowly, grudgingly, violently emerging from physics over the last 50 years is this: not matter, not energy, not space-time, information. The universe is made of information, and I know how that sounds. It sounds like something you would read on a poster in a philosophy department next to a quote from somebody who never did a calculation in their life. So let me be very precise about what I mean, because this is not metaphor and it is not poetry. It is a claim about the physical structure of reality that makes testable predictions, that has survived every attempt to kill it, and that has forced the most hard-nosed people in theoretical physics, people who would never in their careers use the word profound without wincing to take it completely seriously. Here is how we get there. Start with something you think you understand: a black hole, a region of space-time from which nothing, not light, not information, not anything can escape once it passes the event horizon. Now ask a simple question. What happens to the information content of a physical system when it falls into a black hole? An astronaut falls in. She carries information, the pattern of her atoms, the state of her nervous system, the specific quantum configuration of every particle that constitutes her body. What happens to that information after she crosses the event horizon? For a long time, the working assumption was it gets destroyed, the black hole swallows it, it is gone. And this turns out to be one of the most dangerous ideas in the history of physics, because it is in direct and irreconcilable conflict with quantum mechanics. Quantum mechanics is not a theory that allows information to be destroyed. Not sometimes, not in extreme circumstances, never. Quantum mechanics says the total information content of a closed system is conserved always, under all conditions. This is not a detail of quantum mechanics. This is load-bearing. This is the thing that the whole mathematical structure sits on. And a black hole that destroys information is a black hole that destroys quantum mechanics, which means it destroys the most precisely verified theory in the history of science. Now, here is where it gets strange. Stephen Hawking discovered in 1974 that black holes are not actually black. They radiate. When you account for quantum effects near the event horizon, a black hole slowly leaks energy in the form of thermal radiation, what we now call Hawking radiation, and over an enormous but finite period of time, the black hole evaporates completely. And Hawking said, the radiation is thermal, meaning it is random, meaning it carries no information about what fell in. The astronaut falls in. The black hole evaporates. The information is gone. This became known as the black hole information paradox, and it split physics into two camps for 30 years. I was in one of those camps. I'm going to tell you which one, and I'm going to tell you why, and I'm going to tell you about the afternoon in 1983 when I had a conversation that changed the entire direction of my thinking. I was at a workshop in San Francisco. Hawking was there in that extraordinary way he had of entering a room and immediately becoming the room. He was presenting his argument for information loss, and it was airtight by his own construction, internally consistent, beautifully reasoned, and in my judgment, completely, irretrievably wrong. Not because the math was bad, because the conclusion required throwing out quantum mechanics, and I was not prepared to throw out quantum mechanics to save a result that came from a semi-classical calculation. That is exactly backwards. You do not destroy your most verified theory to save an approximation. You go back and fix the approximation. What followed was not a polite disagreement. It was a 20-year war. Hawking on one side, insisting that black holes destroy information, that quantum mechanics would have to be modified, that nature herself permits this kind of loss. 't Hooft and I on the other side, insisting that no information is ever lost, that we did not understand black holes well enough yet to see where the information was going, but that quantum mechanics was not negotiable. We fought this out in papers, in conferences, in arguments that got personal in the way that only physics arguments do, which is to say, completely personal while being entirely about the equations. And eventually, and I will not be modest about this, we won. In 2004, Hawking conceded. He stood up at a conference in Dublin and said that black holes do not destroy information, that he had been wrong, and that information escapes in the Hawking radiation in a scrambled but recoverable form. He showed up at the conference in a t-shirt that said, I was wrong. That is, I want to say clearly, one of the most honorable things any physicist has ever done. But here is what winning that argument forced us to confront. Because you cannot simply say, the information escapes in the Hawking radiation and walk away satisfied. You have to explain how. You have to explain the mechanism. And to explain the mechanism, you have to think very carefully about what it means for information to be encoded on the surface of something rather than in its volume. And this led through a chain of reasoning that I am going to walk you through brick by brick to the single most astonishing result in theoretical physics in my lifetime. Think about a hologram. Not the scientific sense yet, just the everyday object, the thing on your credit card. A hologram is a two-dimensional surface that encodes a three-dimensional image. All of the information needed to reconstruct a three-dimensional structure is present in the two-dimensional surface. No information is hidden in a third dimension somewhere. The three-dimensional object is a kind of projection of the two-dimensional data. Now ask yourself, and really sit with this question before you let yourself answer it. Is this just an analogy, or could it be something deeper? Could it be that the three-dimensional world you experience is itself a kind of projection, and that the fundamental description of reality, the place where the actual physics lives, is on a two-dimensional surface? Here is the concrete argument, and I want you to follow each step, because if you follow each step, you will not need to trust me at the end. You will simply see it. Take any region of space, put it in a box. Now ask, what is the maximum amount of information you can pack into that region? Your first instinct is to say it scales with the volume of the box, triple the volume, triple the information capacity. This is what every reasonable person assumes. This is what I assumed for years. It turns out to be wrong. Jacob Bekenstein, in 1972, working on the thermodynamics of black holes, showed that the maximum information content of any region of space is proportional not to its volume, but to its surface area. The area of the boundary of the region, measured in units of the Planck length squared, the Bekenstein bound. And then Hawking, in one of the great ironies of his career, confirmed this by calculating the entropy of a black hole, which is itself a measure of information, and found that it equals 1/4 of the area of the event horizon in Planck units, not the volume, the area. Every time, without exception, the information lives on the surface. This is a profound and deeply strange fact about the physical world. It says that if you try to pack more than a certain amount of information into a volume of space, you do not succeed. What you get instead is a black hole. The black hole is nature's way of telling you that you have hit the information theoretic limit of that region of space. And that limit is set by the area, not the volume. This is not a consequence of some particular model. This is a consequence of combining general relativity with quantum mechanics in the mildest possible way, and it keeps coming out the same. Volume is not fundamental, the boundary is. I want to give you a thought experiment to make this visceral. Imagine you are trying to describe the complete physical state of everything inside a sphere, 10 meters in radius. Every particle, every field, every quantum bit. According to the Bekenstein bound, the total information content of everything inside that sphere is bounded by the area of its surface, roughly 12.5 square meters worth of Planck areas, which is an enormous number, but it is finite, and it is set by the surface, not the volume. Now, here is the strange part. There is no special physics on the surface of your sphere. You can move the sphere anywhere. Nothing happens at that surface. The boundary is not a place where the world ends. It is not a membrane. It is not anything physical. And yet, the total information that can exist inside it is bounded by its area. What does that tell you about the relationship between the three-dimensional physics inside and the two-dimensional information on the boundary? It tells you that the three-dimensional physics is, in some fundamental sense, redundant, that everything happening in the interior is already described, is already encoded in the boundary data, that the interior is a derived quantity, not a fundamental one. This is the holographic principle. And I want to be very clear, I am not using holographic as a metaphor. I am using it as a precise technical claim about the structure of physical reality. The information content of any region of space is not in the region. It is on the boundary of the region. Space, as we experience it, three-dimensional, volumetric, the thing that contains everything is emergent. It is not fundamental. It is something that appears to exist from a description that does not itself contain it. Now, here is where it gets strange again, and this time it gets strange in a direction that physics has only recently learned to navigate. In 1997, Juan Maldacena published a paper that was, without exaggeration, a revolution. He showed, in the context of string theory, which gave us the mathematical tools to make this precise, that a theory of gravity in a three-dimensional anti-de Sitter space is exactly equivalent to a certain type of quantum field theory living on the two-dimensional boundary of that space, not approximately equivalent, not analogously equivalent, mathematically identical. Every calculation you can do in the gravitational theory in the bulk has an exact translation into a calculation in the non-gravitational theory on the boundary. The two theories are different descriptions of the same physical reality. Gravity on the inside, quantum mechanics on the outside, and they are the same thing. This is what physicists call ADSES, CFT correspondence, and it is the most precise and powerful realization of the holographic principle we have. I need you to understand how radical this is. Gravity in ADSE CFT is not fundamental. Gravity is an emergent phenomenon. It appears when you look at certain patterns of entanglement in a lower dimensional quantum system without gravity. Space-time geometry, the thing that Einstein taught us, is the fundamental arena of physics, turns out to be something that crystallizes out of quantum information. The curvature of space is a consequence of the entanglement structure of the boundary theory. More entanglement, more connected space-time, less entanglement, cut the entanglement between two parts of the boundary theory and the corresponding regions of space-time disconnect. Space-time literally falls apart when you remove the quantum correlations that hold it together. Mark van Ramsdonk did the calculation in 2010. He showed that if you take two copies of a quantum system, entangle them maximally, and ask what the dual gravitational geometry looks like, you get a connected space-time, a wormhole connecting two regions. Cut the entanglement and the wormhole closes. The geometry changes, space disconnects, and I want you to sit with what this means. Space-time connectivity is entanglement. The reason the room you are sitting in is a continuous connected space, the reason you can walk from where you are to where I am, is because of quantum entanglement. Not some poetic version of entanglement. The actual mathematical, measurable quantum correlations between the fundamental degrees of freedom of the boundary theory are what is maintaining the geometry of the space you inhabit. I have spent 40 years thinking about these questions, and I will tell you honestly that there are mornings when I come into my office and look at the equations and feel something that I can only describe as vertigo. Not confusion. I am past confusion on most of this. Vertigo. The specific sensation of standing at the edge of something very large and looking down. Let me give you a thought experiment that gets at what this really means for the nature of space. You and I are sitting in this room, separated by some distance. The space between us feels primary. It feels like the most basic, obvious, rock-solid fact of the situation. I am here, you are there, space is in between. But what adds CFT is telling us is that this spatial separation is secondary. What is primary is the quantum information structure, the pattern of correlations and entanglement, and the spatial separation is something that emerges from that structure. Distance in this picture is not a thing in itself. Distance is a property of an information relationship. 2 points are far apart when they are weakly correlated in the boundary theory. 2 points are close together when they are strongly correlated. Space is the geometry of information relationships. This has a consequence that I think about constantly, and that I do not think enough people have properly confronted. If space is emergent from entanglement, then asking what happened before the Big Bang is not like asking what was north of the North Pole. It is more like asking what the information structure of the universe looked like before the degrees of freedom that give rise to space-time were entangled in the way that produces the space-time we inhabit. It is a question about quantum information, not about geometry. And we might actually be able to answer it, because quantum mechanics, unlike general relativity, does not break down at the Big Bang. The singularity is a geometric artifact, and if geometry is emergent, the singularity may dissolve in the underlying quantum description the way the North Pole dissolves when you switch from geometry to algebra. I had a conversation, this was around 2012, with a group of younger physicists who were working on this problem, where someone asked me what I thought the Big Bang was at the most fundamental level. And I said, it might be a phase transition, not in space, not in time, but in the pattern of entanglement, a moment when the quantum information structure underwent a kind of transition that produced, for the first time, something that looks like a smooth space-time. Before that transition, there may be no meaningful sense in which there was a before, not because time did not exist, but because the structure that gives rise to the experience of temporal sequence had not yet crystallized out of whatever quantum substrate underlies it. I do not know if this is right. I want to say that clearly. This is the frontier, not the settled territory. And here is my genuine, productive, non-comforting uncertainty. I am not sure whether the mathematics we are using to describe this is adequate. Add CFT is our best tool, but it lives in anti-de Sitter space, a universe with a negative cosmological constant, a very specific kind of curvature. We live in a universe with a positive cosmological constant. We live in de Sitter space. And the holographic principle in de Sitter space, the holographic principle in our universe, is not well understood. We believe it is true. Every piece of physical evidence points toward it. But the precise mathematical formulation, the analog of Maldaceno's dictionary for our actual universe, is not known. This is not a small gap. This is a fundamental gap. And it is the thing that keeps me and a very large number of physicists I deeply respect lying awake at night. Here is another piece of the puzzle that I have not told you yet, because I wanted to lay the foundation first. In 2013, Juan Maldacena and I wrote a paper. The paper is called Cool Horizons for Entangled Black Holes, but everyone in physics calls it ER equals EPR, which is the core claim that the Einstein-Rosen bridge, a wormhole, the geometric connection between two distant or disconnected regions of spacetime, is the same thing as Einstein-Podolsky-Rosen entanglement. Two black holes that are maximally entangled in the quantum mechanical sense are connected by a wormhole in the geometric sense, not analogously, not as a useful fiction. Geometrically, the wormhole is the entanglement seen from the geometric side. The entanglement is the wormhole seen from the information side. I want to think through this carefully with you, because if you take it seriously, it has consequences that are genuinely mind-altering. If ER equals EPR is correct, then every pair of entangled particles in the universe is connected by something. Not a traversable wormhole. You cannot send a signal through it. You cannot travel through it. It does not violate causality. But a connection, a geometric relationship, a link in the fabric of space-time that exists precisely because of the quantum correlation between them. This means that entanglement is not just a property of quantum states. Entanglement is geometry. The topology of spacetime, the question of what is connected to what, the question of what the overall shape of the universe looks like, is a consequence of the pattern of quantum entanglement among the universe's fundamental degrees of freedom. You are connected geometrically to every particle that is entangled with particles you have interacted with. The universe is not a collection of things in space. It is a pattern of correlations that gives rise to the appearance of space. There is a moment in the research, I can tell you exactly when it was, when all of these threads came together for me in a way that produced something I would not quite call understanding, but would call recognition. I was at the Kavli Institute in Santa Barbara. It was late. Everyone else had gone to dinner, and I was sitting with the equations from what became the ER equals EPR paper. And I was looking at the relationship between the entanglement entropy of two subsystems and the area of the minimal surface that separates them in the bulk, the Ryu-Takayanagi formula, if you know it. And I realized that I was looking at the same equation from two completely different directions. And it was the same equation, entanglement entropy on one side, geometric area on the other, and the Planck length sitting there in the denominator tying quantum information to space-time geometry. And the thought I had, which I immediately tried to argue myself out of and failed, was information is not in the universe. Information is the universe, not as metaphor, as the literal statement of what the physics is saying. This is where I have to be honest with you about what we do not know, because everything I have told you up to this point has at least the virtue of being supported by a significant body of evidence and calculation. What I am about to say is more speculative, but it is the direction in which the evidence is pointing, and I would be doing you a disservice if I stopped before showing you the full implication. If space-time is emergent from entanglement, and if entanglement is the fundamental substrate of physical reality, then we need a theory of quantum gravity that is not a theory of quantizing space-time, because space-time is not fundamental. So quantizing it is the wrong approach, but a theory of the information structure from which space-time emerges. This is the deep failure of the early approaches to quantum gravity. We kept trying to take general relativity and quantum mechanics and merge them at the level of the geometry treating space-time as something that should be quantized the way the electromagnetic field was quantized. And it never worked. The math kept breaking. The infinities never canceled properly. And the reason, in hindsight, is that we were trying to quantize something that is not itself fundamental. You cannot successfully quantize an emergent phenomenon. You have to go to the underlying level, the quantum information structure, and show how the space-time geometry emerges from it. This is the program. It is not complete. I will not pretend it is complete. The details of how smooth space-time with its specific properties, 4 dimensions, a particular causal structure, the specific form of Einstein's equations emerges from the underlying quantum information structure is not fully understood. We can see it happening in ADS CFT. We have the map, but we do not fully understand the mechanism by which the map is drawn. We do not have the quantum gravity theory that works in our universe in de Sitter space, with the positive cosmological constant that observations force us to accept. We have an enormous amount of scaffolding and very little of the building. And here is the thing that I find not comforting, but genuinely productively disturbing. The positive cosmological constant dark energy, the accelerating expansion of the universe, may itself be in tension with the holographic picture in a deep way. In anti-de Sitter space, the holographic boundary is well defined. It sits at spatial infinity, and you can talk precisely about what lives there. In de Sitter space, the universe is expanding, observers have finite horizons, and the holographic boundary is not a static surface at infinity, but a cosmological horizon that is observer-dependent. Different observers have different horizons. Different observers in a holographic universe have access to different total information. What does that mean? Is the full quantum description of the universe also observer-dependent? Is the holographic dual of a de Sitter universe a single theory or a family of theories, one for each observer? We do not know. I genuinely do not know. And I do not know of anyone who does, and I have been asking people who would know for a long time. Let me bring you back down to Earth for a moment, or rather, to a very specific point above the Earth. In 2015, LIGO detected gravitational waves for the first time. 2 black holes merging, 1 billion light-years away, producing a ripple in space-time geometry that shook mirrors 1/4 of the way around the world by less than 1,000th of the diameter of a proton. This was not just an experimental triumph. This was the universe speaking in the language of geometry. That signal encoded in the shape of the gravitational wave and the chirp, in the way the frequency increased as the black holes spiraled together, the mass and spin and orbital parameters of the black holes to extraordinary precision, information encoded in the geometry of space-time, traveling at the speed of light, arriving at a detector that read it out. From a holographic point of view, what LIGO detected was information, not a disturbance in a medium, not a vibration of particles. The information content of a space-time geometry propagating through the boundary conditions of a larger space-time. The universe writing in its own fundamental language, and us, for the first time, learning to read it. Here is something I want you to take home. Every physical object you will ever encounter, every chair, every planet, every star, every galaxy, every photon that has ever struck your retina is, at the deepest level we know, a pattern of information. Not a thing that contains information, the way a book contains information. A pattern of information, the way a holographic image is information, not a thing that stores information on a surface, but a thing that simply is the information on a surface, read out into the appearance of 3 dimensions. The 3-dimensional world is the universe's way of displaying a 2-dimensional data set. And the universe is doing this not because it is trying to fool you. The universe is doing this because this is apparently what physical reality actually is. I went into physics because I grew up in the South Bronx in a world that felt very physical, very material, very much a place where the weight and solidity of things mattered. The concreteness of things was real to me. The hardness of walls, the coldness of winters, the specific gravity of circumstances. And physics was a way to understand that concreteness, to get behind it, to find out what it was really made of. And what 50 years of physics has told me, not gently, not encouragingly, but with the blunt force of mathematical demonstration, is that the concreteness is real and it is emergent, and underneath it is something that is neither solid nor material, but is instead a structure of information and entanglement and correlation from which the experience of solid material things arises. And I find this not disturbing in a nihilistic way. I find it disturbing in the most productive sense. It means that the universe is stranger and richer and more intricate than the most ambitious materialist imagined. It means that the solid world is not a consolation prize for living in a quantum universe. It is the quantum universe seen at the resolution available to creatures of our particular size and complexity. One final thought. The holographic principle says that the information content of any region is proportional to its boundary area. The boundary area is finite. The information content is finite. The universe is a finite information system. And a finite information system can, in principle, be described completely exhaustively. Not in practice, the number of bits required is incomprehensibly large, but in principle. The universe has a finite description. It is not infinite in its complexity. It does not go on forever in every direction without structure. It is bounded informationally by the physics of its own surfaces. And this means that physics is not an infinite project. It is a very long, very hard, very contested project, but it has an endpoint. There is a complete description. There is a final theory. And every calculation that has ever been done, every experiment that has ever been run, every argument I have ever had with Stephen Hawking or anyone else has been a step toward that description, not a step toward understanding something alien and external, a step toward the universe understanding itself. Because that is what we are, the part of the information structure that became complex enough to start asking what the information structure is made of. And the answer, as best we can tell, is it is made of the question.